Hi everyone, my name is Nguyen. I'm going to talk about P4-free partition and cover numbers and its applications. This is our work with Alex, Simina, Hemanta, Himanshi, and Tamalika. So let me start with some motivation for our work. Consider a setup where Alice and Bob sample from a Zoe distribution. Alice gets X and Bob gets Y. A Genie who observes the Zoe sample provides a system Z to help Alice and Bob. Alice and Bob's objective is to non-interactively establish a key S, and they also want to extract the leftover entropy from their samples as independent private randomness. The question of interest is, what is the minimum assistance Z needed from the Genie? You can think about the Genie assistant as an information-theoretic measure, and in fact, low-bounding this information-theoretic measure translates into communication and cryptographic low bounds of interactive protocols. The Genie's assistant can be equivalently replaced by a communication protocol between Alice and Bob. Or you can think about it at any arbitrary functionality. And here you can make multiple calls to this functionality and get the outputs. So for example, the functionality at ICE can be the off-previous transfer or the NAND gate, which we know are sufficient for general skill computations. And next, for the second application, consider a similar setup where parties get a sample from a Zoe distribution and they can communicate with each other. However, Alice and Bob objectives is different from the previous application. So you want to get a secure random sample of an off-reverse transfer. So Alice outputs two random bits R0 and R1, while Bob outputs two random bits B and RB. So in this model, Bob also gets lambda bit leakage from Alice shares X and vice versa. Alice also gets lambda bit leakage from Bob shares Y. So we are interested in the maximum leakage resilience of secure computation protocols. And it turns out that this is related to the P4-free partition number. And the third motivating problems is in communication complexity. Suppose we want to compute a Boolean function related to the equality oracle. So in this model, Alice has input X and Bob has input Y. So you also get some non-deterministic input Z. Based on some private inputs and the non-deterministic input Z, Alice computes some X prime and Bob computes some Y prime. This is done without any additional computation. Then these values, X prime and Y prime, are served as inputs to the equality oracle. So the output of the equality oracle is 1 if X prime and Y prime are the same and 0 otherwise. And these pictures define a non-deterministic protocol for the Boolean function f if for every input pair X, Y, so that the evaluation of the function on that input pair is equal to 1, then there exists a non-deterministic Z ensuring that the output is 1. Otherwise, if f of X, Y equal to 0, then there is no sub G, leading to output being 1. And the communication complexity of the protocol is the size of the support of Z. So our interest is to find the communication complexity of a Boolean function f in this model. And this motivates us studying the P4-free covered number. So far, I have briefly described motivations for studying P4-free partition and covered numbers. So what are they? Let me introduce some basic notions before discussing them. A P4 graph is a graph with 4 vertices, forming a path of length 3. And as you can see in the picture, so we say that the bipartite graph is P4-free if no 4 vertices induce a P4 subgraph. It means that each connected component of the graph is a bicyclic. A bicyclic is shorthand for complete bipartite graph, in which every vertex on the left bipartite set is connected to every vertex on the right. In literature, there's some other names for P4-free bipartite graphs. It was so known as closed graphs, complement reducible graphs, hereditary district graphs. And here is some intuition for P4-free bipartite graphs. A P4-free bipartite graph can be thought of as a disjoint union of bicyclics. For instance, in the picture on the left, it is a disjoint union of 3 bicyclics. And each shaded region represents a bicyclic. Intuitively, if looking at the adjacency matrix, a P4-free bipartite graph is a disjoint union of rectangle. And matching star forest bicyclics are some special cases of P4-free bipartite graphs. Our work also encodes joint distribution of Boolean functions as bipartite graphs. So a flat distribution is a uniform distribution over the support. So let me give you an example. The forward of flip O distributions E over NB string times NB string. For this distribution, Alice receives uniform and independent NB string. Condition on Alice sample, Bob either received the same NB string with property half, or received the flip of all NB string with property also half. So a flat distribution can be represented as a bipartite graph. So the left bipartite set is a sample space omega A. The right bipartite set is a sample space omega B. And the X set is a support of the distribution XY. And here is an example of the forward of flip O distributions for n equal to 2. So it is of 4 by 4 matrix in the adjacencies representation. So at this point, one might wonder how P4-free graphs are relevant to the application we have discussed earlier at the beginning of the talk. So for the application of establishing shared key and randomness injections, it is natural to ask which joint distributions do not need any Genie assistance at all. So our primary observation is that a flat joint distributions needs no assistance if and only if the corresponding graphs is P4-free. The forward of flip O distributions for n equal to 2 is an example. Clearly, this graph is P4-free since it is a disjoint union of 2 rectangles, and the TS is the XOR of the 2 bits. Okay, so for Alice, it is the XOR of X1 and X2. For Bob, it's the XOR of Y1 and Y2, and they are the same. And Alice and Bob private randomness can be derived by outputting their first bit. Okay, so the I equal to X1 and IB equal to Y1. And this can be generalized to any P4-free graph. So shared key is the identity of the connected component. And condition on the identity of the connected components, Alice and Bob's samples are uniform and independent. This is easy to see because they are distributed according to the uniform distribution over the bicyclics. Another property of P4 graphs is that it had no leakage resilience. So starting with samples from a P4-free graph, it is impossible to perform general CQ computations. In other words, any protocol for general CQ computation is insecure without any leakage. And for the third application, interestingly, every P4-free Boolean function has zero non-deterministic communication complexity relative to the equality oracle. Why is this? Suppose a Boolean function f is P4-free, given x, at least compute x prime as the identity of the connected component containing the vertex x. Similarly, Bob computes y prime as the identity of the connected component containing the vertex y. And it is easy to see that the output of the equality oracle is exactly identical to the output of the function f. So now the question is that what if the Lie distributions of the Boolean function is not P4-free? So what if it is a general graph? So how would the answer change? So it turns out that the answer is related to P4-free partition number or the P4-free cover number. So let me start with the P4-free partition number first. The P4-free partition number of a bipartite graphs is the minimum number of P4-free graphs that is needed to partition the X set of the given graph. So clearly, if the graph is P4-free, then its P4-free partition number is 1. One such example is a forward of triple distributions. So let me give you another example. The noisy tri-vector distributions gives Alice a random empty string X and condition on Alice sample of either receives the same empty string with property half or receives X plus 1 modulo 2 to the power of n with property also half. And clearly, this is a flat distribution. And note that it graphs your cycle. And the P4-free partition number of noisy tri-vector distributions is 2 for any n greater than or equal to 2. And here you can see the partition when n equal to 2. So the adjacency matrix can be partitioned into disjoint unions of the two rectangles. So how the P4-free partition numbers is related to Shaky and randomness interactions. Our primary observation is that the size of Genie assistance support must be at least the P4-free partition number of the graph corresponding to the flat Zoid distribution. And furthermore, the equality is achievable. And intuitively, for any small z in the support of Genie assistant, the conditional flat distribution xy condition on the random variable equal to small z, it is P4-free. So the graph G is partitioned into P4-free subgraphs based on the support of Z. Okay. So that's why we have this primary observations. So for measuring the Genie assistant, we note that existing information-theoretic and covering measures are not really precise. So for example, the forward of RIP-O or the noisy tri-vector distributions have the same mutual information. And it is MS1 for both of them. However, they require different Genie assistance. So the size of Genie assistance support is 1 for the forward of RIP-O distributions, and this is 2 for the noisy tri-vector distribution. So Weiner's common information is also significantly overestimated. And if we look at the gas corner common informations, it is somehow too pessimistic and seems unrelated. Covering measures like by-click partition or cover numbers are so imprecise. And so this covering or partition numbers is related to Weiner's common informations. So our first graph theoretic result is that determining the P4-free partition number of bipartite graphs is NP complete. And our main ideas is reduce the non-NP complete problem, star aposity of bipartite graph, to this problem. So as a consequence, finding the minimum Genie assistance is difficult in general. Next, can we construct graphs with high P4-free partition number? The answer is yes. We show that there are bipartite graphs with side and partisets, so that the P4-free partition numbers are at least epsilon times n to the power of 1 minus 2 epsilon for any constant epsilon that is an inverse of a positive integer. So as a corollary, for any t very positive integer, there are Zoid distributions over NB string times NB string that require 1 minus 2 divided by t plus 2 n bits of the Genie assistance. So here it requires linear number of bits for the Genie assistance, and the constant is quite large. And if we let t to be very, very large, and it's very close to n. Now let's discuss the P4-free cover number. So the P4-free cover number of a bipartite graphs is the minimum number of P4-free subgraphs that is needed to cover the exit of the given graph. So you can see here, the only difference from the P4-free cover number and the P4-free partition, it is a cover instead of a partition. So obviously, the P4-free cover number of a graph is way less than or equal to the P4-free partition number of the same graph. So let me show you the connection to non-deterministic communication complexity. So we show that the support of the non-deterministic input Z must be at least the P4-free cover number of the bipartite graph corresponding to the Boolean function f. Furthermore, the equality is achievable. So let me give you some intuition. So for non-deterministic input Z, fixed Alice strategy and also fixed Bob strategy. Now, if we look at any small z in the support of the non-deterministic input G, the bipartite graph of input pairs that lead to output being 1 is P4-free. So we can see that the bipartite graph G is covered by P4-free subgraphs indexed by the small z in the support of the random variable capital Z. And similar to the hardness of P4-free partition number, we prove that determining the P4-free cover numbers of bipartite graphs is also NP complete. And basically, we use the same idea. So as a consequence, finding the minimum size of the non-deterministic input required by parties in the communication complexity model is difficult in general. And next, we also show that we can construct bipartite graphs with high P4-free cover number. So this theorem, it looks quite similar to the theorem of the graphs with high P4-free partition number. And actually, we can use almost identical constructions. And as a corollary, for any positive integer t, there are Boolean functions that require at least 1 minus 2 divided by t plus 2 log space to capital N bits of non-deterministic input in the communication complexity model, whereby t have access to the equality oracle. And finally, we accurately estimate P4-free partition and cover numbers for some well-studied Boolean function in circuit complexity. So let me introduce those functions. So set deterministic function takes as input two sets, and the output indicates whether they are disjoint or not. So the set intersection functions is a complement of the set deterministic functions. We also look at the inequality function. It takes as input two numbers. It outputs 1 if they are not equal, and outputs 0 if they are equal. So we prove that the P4-free partition and cover numbers of the inequality graphs are the same, and they are equal to log ratios of capital N. Next, we also prove the lower bound and upper bound for P4-free partition number and P4-free cover number of the set disjoint function. Okay. So roughly speaking, the P4-free and the P4-free partition number and P4-free cover number is 2 to the power of theta n. So they are exponential in n. And finally, and most interestingly, we prove that the P4-free cover number of the intersections functions is roughly n. And the P4-free partition number of intersection functions is 2 to the power of n by 2. And here, as you can see, the P4-free cover numbers is linear in n, but the bound for the P4-free partition number is exponential in n. So it suggests that there might be exponential gap between the P4-free partition number and the P4-free cover number. So we use different techniques to prove this upper and the lower bound. For more detail on our bounding techniques, please see our paper. Let me wrap it up. We present three main graph theoretic contributions. The first result is to show that computing P4-free partition of the cover number can be complete even for bipartite graphs. And second, we establish correlation to Van-Kiewicz problem to show that there are bipartite graphs with large P4-free partition or cover number. And finally, we accurately estimate the numbers for bipartite graph encoding well-studied Boolean function from circuit complexity. We also present representative applications of this graph theoretic measure. So the first applications is assistance for establishing circuits and private randomness. And the second applications is for non-deterministic communication capacity related to the equality oracle. We also discuss some other interesting applications in our paper. And thank you for listening.